All right, in section 2, we're going to use what we call differentials. Now, differentials is going to be a way to approximate change in a function. So we're first going to look at what we call a tangent line approximation. So a tangent line approximation is when we are going to use a linear function to approximate a function in a certain region, to approximate a function, we'll call it f of x, in a region. So what this essentially looks like, so let's say that we have some curve, and let's say this curve is called f of x. So this is my curve, something like this. So if I have a point C here, then if I take this point up here, then this y value in f of x is f of c. So we can consider this point here c comma f of c. So when I'm trying to do a tangent line approximation, it's what we've done for a while in this course, where we find the tangent line at this point. And now instead of just using this tangent line, at points very, very, very close to C, so if I'm taking points a little bigger, a little smaller than C, instead of looking at them on this function, we can actually look at them on this line. So the tangent line is very easy. So the tangent line approximation for f of x, we can just kind of summarize what we did before, and it's simply going to be y minus f of c equals f prime of c times x minus c. So this is the tangent line approximation at some point c, and obviously the y value being f of c. So we can see how good this is. We can find derivatives, and we can do all this stuff to find the tangent line approximation, and then we'll see how close it is to our actual function. So if I want to find the linear approximation, tangent line approximation to this function at the point x equals 0, and it is important to remember this is really happening at a certain point, because obviously if I have this red tangent line, I don't want to go over here and be using the tangent line. If this is C, I don't want to use the tangent line way up here. So you want to use the tangent line at points pretty close to your C. So the first thing I'm going to do is if I'm going to find a tangent line approximation, and to do that, we're going to first find the derivative so we can find the slope. So f prime of x for this function. Now remember, this function f of x equals square root of 1 plus x is the same as 1 plus x to the half power. So it's going to be 1 over 2, 1 plus x to the minus 1 half. Technically, there's an inside because it's not just x, but the derivative of 1 plus x is just 1, so nothing really comes of that. If it was 1 plus 2x, then obviously that would be something a little different. So if I simplify, this is going to be 1 over 2, and then again, the negative exponent will drop to the bottom, so that's going to be square root of x plus 1. So to find it, since my c value is 0, I am going to use my f prime of 0 for the slope. So this is f of c. That's this part in the function. So f prime of 0 is going to be 1 over 2 times the square root of 0 plus 1, which is 1 half. The only other thing I really need, I have this, I know c is 0, I need f of c as well. So f of 0 is my original function at 0, so that's going to be 1 plus square root of 1 plus 0, which is square root of 1, which is 1. So I have my slope, I have my f of c value, which is this, so I can find my linear approximation. I am going to call it t of x to represent tangent of x. So that is going to be, well, let's go ahead and do it first, and then we'll make it t of x. So we'll do y minus f of c, which is 1, equals f prime of c, which is half, times x minus 0. I mean, technically it's in parentheses, but the 0 goes away. And so then I'll add 1, so y equals 1 half x plus 1. So written in function notation, this is 1/2 x plus 1. Now, I don't know about you, but I would much rather deal with this function here, 1/2 x plus 1, than the square root of 1 plus x. So the question is, how good of approximation is this? How good is my approximation of square root of 1 plus x? How good of approximation is this tangent line function? So if I look at some of these values from this tangent line approximation and the actual function, so if I look at the function, so if I plug in negative 0.1 and negative 0.01 and 0, things really close to it, the values I get are 0.94868, and then I get 0.99499, and then I get 1 there, and then I get 1.005 and 1.0488. So we'd want our tangent line approximation in this area to have values that are very similar, because if it's not a very good approximation. But if I plug in these same x values to our tangent line here, what you see is we'll get 0.95, 0.995, 1, 1.005, so that one's exact, and then 1.05. So if I compare these line by line, you could see that these are all pretty much the same. Really close. So the tangent line approximation using that tangent line is a really good approximation for my function. Now, another thing we can use this for is not only to find the approximate value of the function, but to find a change in a function. So this change can be talked to by what's called a differential. So if you remember our initial talk about derivatives, we talked a lot about dy dx, and dy was change in y versus dx, which is the change in x. So when you talk about a differential, we're trying to talk about the change in a y value when an x value changes. Now the way we write this is, since we know dy dx is the same as f prime of x, the way we generally write a differential is we write it as dy equals f prime of x dx. So it's almost like we're multiplying this dx to the other side. So what this is really talking about is saying the change in y is going to be the derivative at that x point times the change in x. That's going to tell us what our change in y can be estimated with this differential. So we can see how good of change this actually is. We'll look at a couple examples where we find the differential, and then we'll see how good of it is at estimating the change between one value and another. So here is a problem, h of x. So the differential, pretty straightforward. So dy dx of this function, you can think of as y equals x cubed, is going to be equal to 3x squared. So dy is going to equal to 3x squared dx. So what we want to do is we want to calculate and compare the values of delta y and dy. And that's going from x equal 2 to delta x equal 0.01. So let's talk about what this means. So this is saying our x value starts at 2.00, and it's going to change to 0.01. So we're trying to see how much does the function change from 2 to 2.01. Well, to do this, we can find the y value at 2. So the y value at 2 is going to be x to the third. So the y value goes from 8, and then the y value at 2.01, because I'm going to basically plug this value into the cubing function. So 2.01 to the third power is going to give me 8.120601. So my delta y, my change in y, so it's basically how much did it change from 8 to this. So when I plugged in 2 to when I plugged in 2.01, how much did the y change? And that's 0.120601. That's how much it changed. So nothing too complicated. I had to plug in 2, and then I had to plug in 2.01 to get the change in y. Now dy, what we're going to do is we're just going to use this differential over here to approximate that change. So the goal is to try to get a change or something really close to that change without having to do all that work. So if I think of my differential, dy equal 3x squared dx, well, my dy is going to be an approximation of delta y. So my x value is 2, so I'll just do 3 times 2 squared dx. Now dx is going to be how much does the x change? Well, we know how much the x changes. The x changes is going to be the same as this. It's going to be 0.01. So if I do this value, if I do 3 times 2 squared times 0.01, I will get 0.12. So you'll notice using the calculus differential and just plugging in numbers, I get a pretty good approximation from the change from the actual y value from the ending from the beginning ones. So it's just ways, all these differentials are just ways to approximate these different values. Lots of applications of this. We'll see some applications where we do square roots without a calculator. That's kind of a neat application. And there'll be some other word problems and such that we will see in subsequent sections. Let's look at one more example where we're finding this delta y. So we have f of x equals x cosine x. So this one is kind of a harder derivative because it's going to be product rule because we have f of g, f prime g plus g prime f. So if I find dy dx for this one, the product rule says this will be 1 times cosine x plus g prime, the derivative of cosine, remember, is minus sine x, times f, which is just x, so I'm going to put that there. So dy, my differential, is going to be cosine x minus x sine x times dx. So that's my differential. So we can approximate that. Now this is a really tricky one because if I want the actual function, I'm going from x equal pi, and my delta x is 0.01, so if I add that to pi, I get pi plus 0.01, some even weirder decimal, right? So my y values, I'm going to first plug in pi to my function. So that's going to be pi times cosine of x. Or, pardon me, I'm going to plug in pi for that one too. So I'm just plugging this in the original function. So my y value goes from that to my new y value when I plug in my second value is going to be pi plus 0.01 times cosine of pi plus 0.01. Now this looks like a real pain, so I really don't, and I'm really not super excited about having to figure these values out, so that's another good reason where we would love to have an extra way to do this. So this is going to go from negative 3.14, and then my new value, if I add the 0.01, to, if we approximate with a decimal, it goes to negative 3.15. So my delta y, how much it's actually changed, is negative 0.01. It's gone down 1/100th of a unit. And again, I did round that. Now that was a real pain because I had to put this in the calculator, figure out what those values are. But if I approximate it with my differential, dy is simply going to be plugging in pi. So that's going to be cosine of pi minus pi times sine of pi times 0.01. Well, look how this works out. The sine of pi is 0, so this whole term is 0. The cosine of pi is negative 1, so we get negative 1 times 0.01, which equals negative 0.01. So this one, pretty much the same if you go to the nearest hundredth. So again, we're just trying to figure out, estimate the difference in the y values. You go from one x value to the other. So here is one kind of really cool problem where you can approximate square roots without a calculator. So like if I wanted to put this in the calculator, I could figure out what the square root of 50 is. But let's say I wanted to try to figure out what it is without a calculator. Well, I know the square root of 50 is close to a really nice square root. It's the square root of 49. Square root of 49 is 7. So this is very, very, very close to that. So what I really want to do is if I want to figure out my differential, let's say I'm trying to figure out my differential is if I start from an x of 7 and I'm going to make delta x equal to 1. Because if I go from, or pardon me, I did that totally wrong. If we're going from an x of 49, because that's inside my root, then my delta x would be 1. Because that's saying I'm going from 49 and I'm going up 1, that will give me my 50. Well, why is that going to help me? Well, if I say f of x or y is equal to the square root of x function, because this is all talking about the square root of x, when I take the derivative, again, this is x to the 1/2 power, so this is going to be half times x to the minus half. So dy is going to be 1 over 2 square root of x, if I drop that x to the bottom, dx. So it's really just taking the derivative and then multiplying your dx to the other side. Well, if I take the function, if I take f of 49, the function value at 49 is 7. So now, if I want to approximate what is f of 50, all I want to do is how much do I have to add on to this 7 to get to the square root of 50? Well, I can approximate that change with dy. So if I put in square root of 49, because my x value is 49, and my differential is 1, because I'm going up 1 unit to go from 49 to 50, this is going to turn out to be 1/14, because the square root of 49 is 7, so 2 times 7 is 14. So my approximate value for the f of 50, so if I want to know approximately what is the square root of 50, well, it's just 7 plus this change to go from 49 to 50. So it's really, really close to 7 and 1/14. So the square root of 50 is very, very close to 7 and 1/14. Now, if I put 7 and 1/14 in my calculator, I get 7.071428571. And if I actually put the square root of 50 in my calculator, so the actual value for square root of 50 is 7.0710678. So you can see using this method, we were basically the same for 3 decimal points going this way. So this is a really, really neat method, because all you do is you just figure out how far are you away from a perfect square. So we can use this differential for any square root. So this is like the most famous differential, because approximating square roots, really the only way we had to do that up to this point in mathematics is to use the calculator. So if we want to use 120, what square root is close to 120? Well, that's a good question. Well, I know the square root of 121 is 11. So if I make x equal to 121, then I can make my change in x, or my dx, equal to -1. Because if I go from 120 and go backwards 1, I end up at 120. So if I want to know what that's going to be, so I know that f of 121 is 11, because the square root of 121 is 11. So my differential from above, we could say dy is 1 over 2 times the square root of 121 times dx, which is -1. So my approximate differential is going to be, this is 11, so this is 1/22, so it's -1 over 22. So my approximate value for f of 120, or the square root of 120, well, I'll take where I was at 121, which is 11, and then I'll subtract that change in y. So that is going to be simply 11 minus 1 over 22. Now, if I do that in fraction form, that's going to be 241 over 22. Now, how close did I get? Well, 241 over 22 is, so this gives me about 10.9545 repeating. And the actual square root of 120, if I put that in the calculator, I'm getting 10.954451115. So pretty close. So we're approximating it really close to what the actual value is. So these differentials are a really neat way, and really what it's really helping us do is to approximate functional values and some other things without having to use the technology that we usually do. Okay. Well, if you have questions, obviously let me know about this, and we'll certainly get some practice in on this stuff.